All right, let's take a look at lesson 1.2, the limit of a function. So we're going to start off with this investigation, taking a look at the behavior of the function f of x is equal to x squared minus x plus 2 for the values of x near 2. When we enter the function y equals into our calculator, use the as feature in your graphing table, and then we can pull up a table set to find what all of these values are in order to legitimately just plug in, okay, I want 1.0 for x, 1.5 for x, 1.8 for x, 1.9 for x, so on and so forth. If you're having troubles with this, then come and see me in class or in tutorial time. So when I put this in and I'm select my table of values, then I can say that if I use this function and I put in 1 for x, my f of x or my y value winds up being 2. When I put in 1.5, I get 2.75. When I put in 1.8, I get 3.44. At 1.9, it's 3.71. 1.95 is 3.8525. 1.995, I get 3.985. And at 1.999, I get 3.997 approximately. We can see, based on the pattern, that as x is getting closer and closer to 2, approaching from the left, then f of x is getting closer and closer to 4. What about if we approach from the right? So start above, and we're going to start with 3. So we're going to use the same logic. We're going to plug in for the ask so that we can calculate on our calculators. Everything should already be set up. And then when I start with 3, I get 8. At 2.5, I get 5.75. At 2.2, I get 4.64. 2.05 is 4.1525. 2.01, I get 4.0301. At 2.001, I get 4.003. And at 2.0001, I get 4.0003. So as I'm approaching 2, from the right-hand side, f of x is getting closer and closer to 4. And as we can see, as we approach from the left or we approach from the right, we wind up with the same value. So in summary, we say the limit of the function f of x is equal to x squared minus x plus 2 as x approaches 2 is going to be equal to 4. The way that we'd write that is like this. The limit as x approaches 2 of x squared minus x plus 2, or the function, is equal to 4. In general, for any limit, the limit of f of x as x approaches a is going to be L, or the limit of f of x as it approaches a equals L. Roughly speaking, this says that the values of f of x become closer and closer and closer to the value of L, or the number L, as x gets closer and closer and closer to a particular number a from either side, from the left side or from the right side, but x does not actually equal a. Notice that with the phrase x can't equal a in the definition of a limit. This means that in finding the limit as x approaches a, we never consider x to actually be equal to a. In fact, f of x need not even be defined when x is equal to a. So like when we were looking at the last lesson, where if I said that, I had the slope was 9 over 3, and I tried to use the same point, 9 over 3, and I wound up dividing by 0, then it is undefined. So even if it is undefined at this point, the limit still works. All that matters is how f is defined near, or as it is approaching a. Let's try that for this example. When it says, determine the limit as x approaches 3 of the function x minus 3 over x squared minus 4x plus 3. Now remember, you're going to do the same thing. You're going to use the table function in your calculator, and you're going to find what the values of these points are by using the ask function from the table set. If I substitute in 2.5 for x, then the function is equal to approximately 0.66667. If I substitute in 2.9 for x, I get 0.52632. As I keep going, I get 0.50251 or 0.50025, 0.50003, and I'm getting closer and closer as I'm approaching from the left to the value of 0.5 or 1/2. If I am approaching from the right, so I go above 3, starting with 3.5, I get 0.4. At 3.1, I get 0.47619. At 3.01, 0.49751. 3.001 is going to be 0.49975. And 3.0001 is approximately 0.49998. And as I'm approaching, or as x is approaching 3 from the right, it's getting closer and closer to 0.5 or 1/2. Now the notation for when we're approaching from the left is we'd state that the limit as x approaches 3 from the negative side, or from the left. The other case would be the limit as x approaches 3 from the positive side, or from the right. Now it's important to note, as it states here, a limit only exists if the left and right limits are both equal, which means that for the limit to exist, the x as it approaches a from the negative has to be the same as x as it approaches a from the positive. In this case, for the one that we just did, if x approaches 3 from the negative and x approaches 3 from the positive, I wind up with the exact same value, then that means that for this function, we can state that the limit as x approaches 3 of f of x is in fact 0.5 or 1/2. If you enter x is equal to 3, you discover a hole in the table since the function is not actually defined at the point x is equal to 3. When it says show algebraically why it is undefined at x is equal to 3 and what is another name for a hole, well, first I'm going to start by showing algebraically why it doesn't work. I'm going to take my function, and my function f of x is equal to x minus 3 over x squared minus 4x plus 3. I'm going to factor the denominator, x minus 3, and that's going to become, when I factor two factors of 3 that add up to -4 are x minus 3 and x minus 1. We can see that we have our non-permissible values. X cannot equal 3 or 1. What's another name for this hole? We refer to it as a point of discontinuity, or POD. In summary, from the tables above, we can see as x approaches 3, f of x approaches 1/2. This can be verified algebraically. If we take the limit as x approaches 3 of the function x minus 3 over x squared minus 4x plus 3, we're going to factor it like we did above. The limit as x approaches 3 of the numerator stays x minus 3. The denominator gets factored, x minus 3 and x minus 1. And we can remove a common factor of x minus 3 from the numerator and denominator. This means the limit as x approaches 3 is going to be 1 over x minus 1. And then we can use what it's approaching, 3, to substitute for x. 1 over, if x is 3, minus 1, then we wind up with 1/2. If we're using the same principle to determine the limit as x approaches 3 of the function x cubed minus 2x plus 1, then we can just substitute in the value of x. 3 cubed minus 2 times 3 plus 1, and that's going to give me 22. Now, the reason why I don't have to worry about it, like in the previous example, we had that hole that existed because of our rational function. We had the rational function where, because of that point of discontinuity, or the non-permissible, we had that hole at the point of 3 where we were approaching it from both sides, but couldn't actually equal 3 in our original function because it was a non-permissible value. In this case, with this cubic function, the point that we're approaching as x gets closer and closer to 3 and y is equal to 22 is in fact not a point of discontinuity. It would exist on my graph.